method we're going to describe here is called the midpoint method. This is a method also to solve um, the first order ordinary differential equation. This is the ordinary differential equation we do have. This is the equation. And again, this is the initial condition. And the main difference with respect to the two previous methods, both the backward and the forward method, is the accuracy of the method. We want to go one step further in the accuracy, and here, as we'll see later, the error of each step is to delta t to the cube, as we'll see later. That's the main difference. So actually, the strategy that we're going to follow in order to derive that method, actually it's going to be the same strategy for all the methods, is that we're going to use the Taylor expansion again for in order to derive the method. But we're going to use the Taylor expansion, and this Taylor expansion will be made, as in the previous methods, around at point time ti, actually around time ti. But we're going to do that, actually we're going to make two Taylor expansions, and that's going to be crucial in order to go a step further on the accuracy of the method. So we're going to make two Taylor expansions. First one, in order to have the value of the function y evaluated at time ti plus delta t. Actually, this is what we call y at I plus 1. And another one, in order to have the y function evaluated at time ti minus delta t, which is what we are calling y I minus 1. Okay, so we're going to do directly the Taylor expansion, and we're going to make the substitution with time ti. So doing that, in order to have the first Taylor expansion, in order to have this one, this function here, this is the Taylor expansion actually to have the y function evaluated at time I plus 1. So this is the expansion here. So the first term here is the y function evaluated at time I plus delta t times the derivative of y with respect to t, and this is actually the f function as it said, as it's writing in the in our first order ordinary differential equation. Plus, here we're going to go one step farther in the order of the Taylor expansion in order to get a better accuracy in delta t. So we're going to go to higher power in delta t, and the next term here is going to be 1/2 delta t squared times the second order derivative of y with respect to t, and this is actually the first derivative of f with respect to t. And this is this term here. So here, this f prime basically means here the second order, is the first derivative, that's the definition, is the way of writing the first derivative of f, in this case with respect to time, and this is actually the second derivative, considering this, considering that the derivative of y with respect to t is called f. So the first derivative of f with respect to time is going to be the second derivative of y with respect to time. So f prime is the second order derivative of y with respect to time. So this is this is the second, this is the third term here in the Taylor expansion. So we are going to cut here in this order, Taylor expansion, so that the error is going to be to the order of the error here is delta t to the third power. So as a next step, we are going to do actually the same, but here we are going to use the Taylor expansion in order to have an expression for y, in this case evaluated at time I minus 1, so, which is the one we do have here. So actually we have the same expression as the one we do have here above, but the only difference is that in this case delta time is negative as we are going backwards with respect to ti, so that delta t is negative. That's why, that's the reason of having this negative term here. Delta time is negative. In this case, delta time is also negative, but as it's going to the square of delta t, so then it's the, the sign actually is going. It's the same as the one we do have above here. So this is the expression we do have for the Taylor expansion we do have for the evaluation of the y function evaluated at time I minus 1. So once we do have these both expressions here, we are going to make one minus the other. We're going to make one minus the other. Why we are going to make that? Because if we're going to do that, so as you can see here, uh, on the left we do have this minus this one. This is what we do have here. And then these two terms vanishes because we have one minus the other, and they both have the same sign. So these two terms, they have 2 times delta t times f, and these two terms again they vanish because they have the same signs. So that's a way of eliminating these delta t contributions here. But and therefore the order of the method, which is this one, remains to be delta time to the cube. So as you can see here, the error, therefore the accuracy is going to be better. The order of the error is going to be higher compared with the backward or forward methods. So that's basically the results, because the only thing we do have to do now is basically just clear the expression for the y evaluated at time I plus 1. Therefore, we are going to bring this term to the other side. In doing that, this is finally the result we do have for the method. This is actually the result we do have for the method. The thing is that, for example, again, the strategy is actually the same, is that once we know which is actually that the function evaluated at time t naught is actually e naught, then the strategy is to use that in order to have the value of the y function evaluated at time t1. But actually, it's interesting to see that here, when we are doing that, and when we are applying that this method for I equal 0, so we have that I1. This is actually the one we want to evaluate. It's equal to I minus 1 plus 2 times ft0 e1 times delta t. This is what we do have. Okay, we do know this. We do know which are these ones. We do know this one. That's okay. But the thing is that we don't know what's the value of the y function evaluated at minus 1. So the initial point, when we apply initially that method, it makes brings us with this trouble that we do need to know which is the value of the y function evaluated at the previous time at minus 1. Because once we do have that, then we can apply that in order to have the I1, the Y1, and then once we do have the Y1, we can apply again in order to have the Y at time T2 and so on and so forth. But initially, we do have such problem. So it requires some special initialization to generate additional values that are needed from the past. So we need to initialize, so we need to bring, in order to apply that method, the value of the y function evaluated at time minus 1. And how we are going that? We are going to do, in order to do that, basically we're going to apply a very simple, the simplest Taylor expansion we can do for that. So just consider Taylor expansion around t0 and apply that to evaluate the times the y value at time t0 minus delta t, and this is what we called time minus 1. And doing that, in this case, again, delta t is negative. That's why we do have, let's consider linear expansion and Taylor expansion. We do have a negative contribution here. And that's the additional or the special initialization that this method requires in order to get the y function evaluated at time minus 1. Otherwise, it has no other problem in order to have the other values for the wave function. So again, this is a midpoint method, and because actually it's just using these two Taylor expansions in order to have the values both at ti plus delta t and ti minus delta t, yes, when the Taylor expansion is just made at the middle time, which is ti. That's why this method is called midpoint method. And as you can see here, as it happens with the full method, this is an explicit method as well. The main difference with respect, in this case, with the full method is the order of the accuracy, that in this case it's more accurate on delta t.